In this tutorial, I will explain the implementation of a simple consensus object in the chemical machine using the Chymyst library in Scala. A consensus object I'm considering in this tutorial is simply a function such as decide that we can call concurrently from different threads at the same time or at different times. This function takes an argument, so we can call it with different values, but it always returns the same value in all threads that call it. So in this way it provides a consensus between different threads. So this is not a distributed consensus between different processes connected to each other via network. In this case that I'm considering now, it's a very simple consensus within the same JVM instance. So there is not a problem of one thread possibly getting disconnected from others. They're always reliably connected, so there are very few difficulties in implementing the consensus object in the merely multi-thread situation. So how to implement this? Let's reason about what we need to represent in terms of what molecules we would need to define. So clearly the interface we're required to implement is this function that needs to return a value. So it looks like we're asked to implement a blocking molecule. So suppose we have a blocking molecule called decide, and also let's imagine that all the values have some type X. So then the blocking molecule will take an argument of type X and also return a value of type X. So obviously in the chemical machine, the only way to implement any computation is to implement a reaction that will consume this molecule. So something like this maybe. However, if we define a reaction like this, that only has one input molecule, the result would be that when the molecule decide is emitted from different threads, multiple reactions will start, each with its own copy of the molecule decide. So multiple copies of this reaction will start, and we want to prevent that, obviously, because otherwise we won't be able to decide on a common consensus value. So the only way to prevent such things is to introduce another input molecule into the reaction. So now our reaction, let's call this molecule consensus. The reaction needs to have two input molecules. And then if we only ever have a single copy of the consensus molecule emitted, then they will, however many decide molecules are emitted at once, they can only react with one copy of consensus molecule, and so as a result one copy of this reaction will ever run at one time. Now we also need to represent the information about whether a consensus has been already achieved. This information is a value, and so since the chemical machine requires us to keep all values on molecules, we need to put it on some molecule. So it seems natural to put it on this consensus molecule, since we already decided that we need a second molecule as input. So then why don't we use that molecule to hold the information about whether we already reached a consensus. Now obviously this information is a disjunction of either we haven't yet reached a consensus, or we have, and then we have some specific value which we agreed on. And so this disjunction is clearly an option type, such as option of X. So let's define therefore the consensus molecule having a value C, which will be of type option X. Now, what should we write on the right-hand side of this reaction? If C is none, so C is an option X, so it can be none or it can be some Y. If it is none, we don't have yet a consensus, but somebody already wants to decide, so let's just decide on this value, since nobody else is asking right now. And we are then going to set this X as a value of the consensus and also reply to the decide molecule with the same value X. And if C is not empty, then it means we already have a consensus. So then we have to discard this X. The consensus is Y. So we need to reply with the Y value to the molecule decide, and the consensus is unchanged. So that's basically the implementation. So here's the code. We make a function make consensus object that returns a molecule emitter of this type. So this is a blocking molecule that carries a value of type X and also has a reply of the same type. So we decide, we define a decide molecule. We define a consensus molecule. A consensus is a non-blocking molecule. And then this logic can be implemented very simply like this. So we have this reaction. It will consume 2 molecules. Now we can compute the consensus value, which is the decision value that I called here decision. So this will be C if C is not empty, otherwise it will be X. So this represents this logic. If C is none, then we have X. If C is some Y, then we have Y. So now we have computed this, and we simply reply with that value to the molecule decide using its reply emitter. And we also emit a consensus molecule again, carrying now a decision. Now, after this point, we always have some value of consensus. Nothing else to decide. Now, consensus molecule seems to be a static molecule in the sense that we need to have a single copy of this molecule at the beginning, and each reaction will consume this molecule and again emit it back. So this is a pattern that I call static molecule, in the sense that the presence of this molecule is always assured, and there's always one copy, or a fixed number of copies in general, but in this case it's just one. And so let's declare that it is static right here. And this is the syntax for declaring a static molecule and specifying the initial value. So this syntax looks like a reaction that has no input molecules, and this is a special case for the chemical machine, the Chymyst library, which will then run this reaction exactly once at the beginning. So in this way we avoid errors that consist of not emitting this molecule at all, forgetting about it, or emitting it more than once. So if any of this happens, there will be an error. So finally we simply return this molecule emitter that we defined. So we don't return the consensus molecule emitter. That's important. We don't want anyone else to be able to emit another copy of consensus molecule, because that molecule carries the value that we're deciding on. So using this construction, we have a function in whose scope we define the consensus molecule, and so nobody else could possibly emit that molecule. We cannot have access to this value from outside of the scope of this function. From outside, we can only have access to the decide emitter, because that's what the function returns. So that's a typical pattern in chemical machine programming that we have seen already in several tutorials, that we have a function defining a bunch of molecules and reactions inside and returning just one or some of those emitters that are defined inside, and hiding every other emitter and every other. So we're hiding consensus emitter in this case, because we must make sure that nobody can emit any extra, so to speak, any rogue copies of consensus molecule. That's it. That's actually the entire code. You see there's just one reaction, which is basically 2 lines of code with, well, 3 lines of code for this reaction and some declarations. That's it. That's the entire implementation of the consensus. To test it, let me use this Go routine helper method that I implemented in the previous tutorial, in which I compared the chemical machine and the Go language concurrency primitives. This we will use right now just for testing, because we want to run multiple processes. Each of those would try to achieve consensus by calling decide. So here's the test. We define a decide object or a molecule. Sometimes this is called a consensus object, but it's just a molecule from a molecule emitter. You see, it has this type with integer values. And then we make 10 concurrent processes that each of them calls decide and prints the result. And each of them calls a decide with a different argument. So we have 1 to 10, and this will be a decide called 10 times with 10 different numbers. And if the logic is correct, then they're all going to print the same number. And which number will vary each time. So let's run this. Then we add some sleep time, because these are non-blocking calls. And just for test, we want to see that this actually runs. So we do some sleep. And the result should be like this. We just print 10 times the same number. So let's see if this runs. Yeah, so now it prints a different number. Let me run it again. It prints a different number, maybe each time. So this concludes the tutorial about the simple consensus implementation in the chemical machine. See, this is the entire implementation. Very concise, and also it's important that I arrived at this code by reasoning. I did not somehow just write it down, but I reasoned about the logic that we require, and step by step I arrived at what molecules I need to define and what values they should carry. And then it was clear what reactions we need, and then I was able to write the code very easily, and it works correctly the first time. So, in fact, the first time I wrote this, I forgot to emit the consensus molecule. So, let's see what happens if I do that. Let me comment this out and run. Now, if I do this, the chemical machine will not know that I wanted the consensus molecule to be present, because I did not define it as a static molecule. So this was my initial code that I first wrote. I thought just one reaction that is sufficient. I completely forgot that I need to have a consensus molecule present. And that's seems to be a very typical error, to forget to emit some initial molecules. And that's why it's nice to do them as static molecules, because then you can't forget and you can't accidentally emit more than necessary. So let's see what happens if I run this. Nothing is printed. So this is a typical result. I wrote a program, it is declarative, so it is correct by construction. There cannot possibly be any error anywhere, and yet it doesn't work. So how do I debug this situation? So there are several ways of debugging. The simplest is to print the contents of the reaction site, which can be done like this. So log soup is the method. Perhaps I should change its name to log site. I don't know. But right now that's what it's called. And this will print the contents of the reaction site into which the molecule decide is emitted. So this is the site that has this reaction, consensus plus decide, which is exactly the reaction we defined here. So let's see. So we have molecules decide /b/p 1, 10, 2. So we have all these molecules decide, 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 and nothing else. There's no consensus molecule. Well, of course it's not working. I forgot to emit the consensus molecule. So I could just add code here to emit consensus of none, and it would just start working. Let's see if that is so. Yes. So now it actually told me that the contents of the site after all this is just a single consensus molecule with value 3, which was the consensus right here. Now, that seems to be working indeed. Let me restore this code to what it was before. Now, just one comment about this debugging output. First of all, the order in which the molecules are defined in the reaction is completely unimportant. This debugging output will print them in alphabetical order. Second, the /b indicates a blocking molecule, and /p indicates a pipelined molecule, which is another feature of the Chymyst library, that some molecules are pipelined and they are consumed in the order emitted. The Chymyst library implements this feature in a rigorous fashion. There is a test or a mathematical condition that says whether the reactions defined for certain molecules are such that these molecules can be always consumed in the order emitted. And so the Chymyst library decides, based on that mathematical condition, whether a molecule can be pipelined or not. So whether the reaction site will always consume copies of the molecule exactly in the order emitted, as in a first in, first out queue. It is not always possible to do that, but it is possible in some cases, and we have seen before that decide was printed as /p/b. So decide is pipelined and consensus is also pipelined. So that's something that the programmer does not need to worry about. The pipelining is automatic. It's an automatic optimization that is decided always mathematically correctly. So in all cases when pipelining does not change the semantics of the program, it is implemented. So it is switched on automatically. So that's just to explain what these symbols mean in the debugging output. So this illustrates how you could try to debug your program to figure out why things are not working. Another much more intrusive way would be to set a debugging log level on a molecule. There's a set log level, and the log level is an integer, so for example it could be 2 or 3 or 4. If I run it like this, we will get a lot of debugging output that actually shows how different conditions are evaluated, how decisions are made when the reaction is scheduled, the reaction is started, consuming some molecules, and what are the resulting molecules after that. After you emit some molecule, what molecules you have at the reaction site at each point, at each time this happens. Also, what thread pool this is running on. So there are lots of debugging information that you can get, which will perhaps be useful, but also tedious to trace. But this is kind of a last resort debugging tool where you want to trace every decision made by the reaction scheduler. Actually here, I think we didn't have enough time to actually run anything, because the debugging takes its own time also to print all these debugging messages. Right, so now we have a lot more debugging messages telling you it's deciding reactions, it's scheduling this reaction. So if you think that a certain reaction should have been started but it doesn't work, and you look at this output, you see these molecules were present while it was deciding. So for example, consensus with value sum 1, decide with value 4, decide with value 6, and so on. So these were present when it was deciding reactions, and then it scheduled this reaction with these input molecules, sum 1 with BP4, and so on. So you can trace in great detail what are the remaining molecules, reaction started on this thread pool, and so on. You can trace the execution of the chemical program in great detail if this is what you need. This concludes the tutorial.